Okay, hello everybody. This is test 4, and let's take a look at the answers. It shouldn't be that difficult, hopefully, if you studied. Strong acid. Well, there's binary acids. The binary acids, as you can see, are when you have a hydrogen connected to another element, like hydrochloric acid, hydrobromic acid, hydroiodic acid. These are binary acids. Any of these would do. You should know this from the lab that hydrochloric acid is very strong. Sulfuric acid, H2SO4, is a very strong acid. The other one is nitric acid, HNO3. So any of these guys would do. Okay, so you should hopefully have this in your list. Now, the conjugate acid for the base, CN minus, this minus means that has a lone pair. You don't know about that right now, but this negative, we need to neutralize it. Conjugate acid is where you add an H plus. So if you have an H plus added with a CN minus, what does that do? It neutralizes it to become HCN. That is your acid, HCN. Okay, the conjugate base for this guy, you're taking away an H plus, so removing the H plus, leaves a negative on the oxygen. So the answer would be CH3O minus. Minus, you have to put a negative there, okay? So conjugate base, we would want to have a negative charge because of the loss of the H plus. Okay, now this one with the correct significant figures, pH. In order to find the pH, what you need to do is you gotta go 10 to the negative, to get the pH, you need to have the formula pH is equal to negative log the concentration of H plus. And in your calculator, if you have the Sharp Scientific Calculator, which I highly recommend, you have to go pH. You have to type in the negative log. So there's a plus minus key, and then you hit the log, and then you put in 6.22 times 10 to the negative 4. 6.22 has 3 significant figures in the concentration term. So the pH, if you were to calculate this, getting negative log 6.22, please use the button EXP. It's just above the 7. So EXP, hit that and you hit minus 4. This will give you an answer of 3.206. That would be the answer for this with the correct sig figs. 3.206. It looks like this answer looks like 4 significant figures, but the 3 is a magnitude placement on the pH scale from 0 to 14. That means 10 to the minus 3 is the 0.0001, but this is going to give you that magnitude. Okay, and so these are the 3 sig figs that count for this. The pOH, everyone got this? 14 minus 3.6, 10.4. 10.4 gives the litmus paper a blue color. Not a red color, but blue color. Base is blue. So the word that describes the acid, water as acid or base it's called amphi, like amphibian. We got amphiprotic. Proton is protic. So proton is the hydrogen without an electron. Or you could call it amphoteric. Amphiprotic or amphoteric. Those are 2 words. Amphoteric is more general. That doesn't have a proton in it, but it could act as an acid or base. This next one, all it is a proton transfer. We got a hydrogen right here. That hydrogen escapes the CN, and notice that you have the answer right here, CN minus. So all you have to do is put in CN minus plus the proton transfers to N3. N3 is called an azide ion, and these are the two ions you make. Or these are the this is the cyanide, the conjugate base of HCN, and HN3, the hydrogen azide molecule. You don't need to put the physical states. I don't need that. I just need the product, the two products. You get 1 mark for each product. All right. Rank the strength of the acids. Now, the lower the pK, the stronger acid. So the one that has the lowest number is the strongest acid. So this guy right here, H3PO4, that would be the strongest acid of the series. And then followed by this one, HF is the second. And then you look for the higher, the next number is this guy right here, the HOOH, that's hydrogen peroxide. That'll be number 3, and the methanol will be number 4. Okay, now if you're given the pK, this pK, you go 10 to the negative 3.2. This is called the anti-log, or that will give you the, whenever you look at pK or pH, so 10 to the negative pK or the pH, the power of that, okay, so this is the power of 10 to the negative pK, so you go 10 to the negative 3.2, and you could punch this in on your calculator, so you go second, you hit the second F, and then you go log, and this will give you 10 to the power, and then you hit minus 3.2. What you do is you use the plus slash negative key, and this will give you the value of 6 times 10 to the minus 4. Why did I choose only one significant figure? The reason for this, again, when you're looking at this, the first digit or the first digits before the decimal, they're placement zeros. They're placement of the magnitude scale. And this magnitude scale would be around the -3 to -4 range, and that's what we got. That's the magnitude. And this is the significant figures, which is only one sig fig. So you're supposed to put 6.0 times 10 to the minus 4 into the space. Okay, these questions are not supposed to be tricky. Kw for the autoionization for water. We could have a balanced equation. Autoionization water, 2 ways you could write it. H2O reacting with itself. One serves as the acid, the other one serves as the base, and you put an equilibrium error right here. So we just put equal, because I can't really do this on my computer. H3O plus OH minus would be the answer. I don't know where that guy came from. Okay, so H3O plus OH minus, and I'm just going to put these so that it shows up as superscripts and subscripts. Subscripts here, and here's a superscript. Okay, there you go. Other way you could do it is just put H2O goes to H plus OH minus. The Kw, because these guys are liquids only count as 1. They're not even counted in the equilibrium expression. This is an expression. All it is the concentration of the products, H3O plus or H plus, times the concentration of OH minus. That is the answer for this one. Very simple. We don't include water in our equilibrium expression. It's just the products over the reactants, and these are just the products right here. Okay, so next one is the Ka with 2 significant figures, 4.9 times 10 to the minus 9. The Kb is. In order to calculate this, all you have to do is take Kw is equal to Ka times Kb. And when you take Kw, which is 1 times 10 to the minus 14, given right there, then you could take the value of Kw over Ka is equal to Kb. So what you need to do is you need to take the fraction, or I'm just going to do this for you. So this is just Kw over Ka, which is equal to Kb. Kb. And so you could calculate that 1 times 10 to the minus 14 divided by 4.9 times 10 to the minus 9. Now, I would recommend when you hit on your calculator 1 times 10, type in, instead of type in times 10, go exp, 1 exp to the negative 14 divided by 4.9 exp to the negative 9. And this is going to be 2 times 10 to the minus 6. 2.0 times 10 to the minus 6. Okay, so 2, this is what you want. Enter is 2.0 times 10 to the minus 6. Okay, the next one is the net ionic equation. Remember in the lab when you have AQ, this could be broken down into ions. And I've seen that on your paper, but you have shown me that this is calcium 2 plus aqueous plus 2OH minus aqueous. And then everything that aqueous, it could be broken down into the ions plus aqueous plus Cl 2Cl minus aqueous. This is a full ionic equation, which you are correct to do. What breaks down, I'm just going to put equal for the arrow. This is calcium 2 plus aqueous plus 2Cl minus aqueous. Now, don't break down water. Water stays as a liquid. That does not break down, so this becomes 2H2O, liquid. Just like your precipitation reactions, the solids don't break down. And so our liquid stays intact. So I think I hit the cap lock by accident. Okay, so if you were to take a look at all your ions, I'm just gonna put my superscripts here, 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 okay, and here. I think I should leave those. We'll just complete this. Okay, so now you could cancel anything that is the same negatives. So positives, the Ca2 plus, we could cancel that. Let's get rid of that. We could get rid of the calcium because they're on the same, both sides of the equation. And then we could get rid of the Cl minus. And what do we end up with is the net ionic equation. And you could divide this by 2 so that you get OH minus plus H plus, giving you H2O. So that would be the net ionic equation. Either way, this is correct right here. So either divide by 2 or leave it like this. Okay, that's the net ionic equation for 2 marks. Now, for the reaction given above here, when 1 mole of CaOH2, calcium hydroxide, reacts with exactly 2 moles of HCl, this is called neutralization. We have neutralized the reaction. And the other term in the titration, you've seen this before, it's called equivalence point. It's the equivalence point in the titration. If a solution of lactic acid was found to a pH of 2.2, the equilibrium concentration would be the 10 to the minus 2.2. Again, this is where you gotta take the anti-log or the inverse log, which is 10 to the power of negative 2.2, or 10 to the power of negative pH. And that answer, please give me in scientific notation. So again, you hit second function, then the log, minus 2.2, and we only need one sig fig, so this is going to be 6 times 10 to the minus 3. 6 times 10 to the minus 3 moles per liter. Okay, for the following reactions, for following, this is now part 2, which is the sequential order. What is the mole of sodium hydroxide required? So remember, you could use the triangle if you want. Moles over liters is equal to moles per liter, or liters times moles per liter. So expand the big M to become moles per liter. This is 0.100 liters times, you don't need to show me the calculation here. I'm showing it to you so that you could see when we expand this M to moles per liter, you can see what cancels. Moles over liter, and you could get the cancellation right there, and you get the answer that is supposed to go in here is 0.0850 mole. The mass of sodium hydroxide that's required, you take 0.0850 mole times the molar mass of sodium hydroxide, which is 23 for sodium, 17 for the oxygen hydrogen, is 40 grams per mole. Remember, the moles have to cancel out. So again, the answer in here is supposed to be 0.340 grams. What volume of water? This is a little bit tricky. Now remember, the solution is 0.10 liters. 0.100 liters. Solution volume. The solution is composed of the solute, sodium hydroxide, and water. So what you have to do is you have to assume 100 liters, 100 milliliters is equal to 100 grams of solution. Okay, so once you get that solution, this is composed of 3.40 grams. Oh, sorry, this is supposed to be 3.4 grams, not 0.34 grams. 3.4 grams. The solution is 3.4 grams of solute, which is sodium hydroxide, plus 96.6 grams of water. Now, the brief statement that you're supposed to say is weigh 3.40 grams of sodium hydroxide on a balance. If you want to just put balance, you could leave it like this. Then add enough water. This is the 96.6 mils of water, or 96.6 grams. And you could say add enough water to make 100 milliliters of solution. Remember, the mass of a solid occupies a volume, and the volume is going to be given by the 3.4 grams of sodium hydroxide. The next one is barbiturate acid. Okay, so this is, we could call it H-barb if you want, but we could just keep it like this. The first hydrogen is the acidic hydrogen. And what you want to do here is, well, let's copy this because we'll need it later. The first question is, what is the molar mass? So you look on the periodic table, you calculate 4 hydrogens. So I'm going to do this calculation. So you got 4 hydrogens. Let's do it here. Let's do it here. So there are 4 hydrogens, which is equal to 1 times 4. So 4 times the 1.008. Well, I'm just happy with 1 gram per mole. Okay. And we got 4 carbons. This is equal to 4 times 12 grams per mole. You got the 2 nitrogens. This is equal to 2 times 14 grams per mole. And you got the 3 oxygens, which is 3 times the 16 grams per mole. These numbers you could find on the periodic table. You could put 1 decimal place if you want. The end result is this is going to give you 128 grams per mole of barbiturate acid. Oops, so 128, and you're supposed to put the units here as grams per mole. Okay, and then what give the mole of barbituric acid 9 grams. All you have to do here is take the 9 grams of this barbituric acid and you multiply it by 1 mole. Let's oops. You multiply it by 1 mole divided by 128 grams. Let's just do it the fraction way. I like the fraction way because this is the dimensional analysis. You could see that the units cancel, and this would turn out to be 9 divided by 128, 0.0703. We'll use 3 sig figs because 9 grams is 0.0703 grams, or mole. This will give you the mole. Okay? Now, oops, can't type MOL. Okay. Give the initial concentration of barbituric acid, 9 grams in 325 mils. So we already got the moles. We got the volume. All you have to do is take the moles. Guess I'll do this again. Fraction form. Mole 0.0703 mole divided by 0.325 liters of solution. This will give you a total value of 0.216 molar solution, mole per liter solution. And that's what you're supposed to put in here. Okay? Divide by 5. Okay. The next one is the first H is acidic. Write the chemical equation of the ionization density. This should be easy. Hopefully this would be easy. So I copy this, paste it right here. You could put AQ. Oh no, this would be AQ. So once in solution, and then equilibrium arrow. I'm going to paste this again to accelerate time. The negative charge should actually go on the carbon. Okay, because the carbon has lost the proton. So I'm going to put the negative charge right there. And then what you have to do is you add in the H plus right here. This would be the ionization, or if you want, you could include water. So this plus water. So if you put water here, either way, this is also acceptable by adding the water, and you put H3O plus here. So H plus is the same thing as H3O plus. Either way, it doesn't matter. So now equilibrium expression, Ka is equal to concentration of products divided by the concentration of reactants. So let's quickly put this. This might be a little bit tricky because I can't actually paste this in. I'll just put that in here. Oh yeah, it did it. Okay, this is great. Well, my subscripts are gone though. Okay, so I just put it like this. It's not plus, it's multiply these two terms. And then you put in the concentration of the acid down here. Again, it's a little bit tricky because the way this word is set up. I can't put superscripts and subscripts like I normally do because it's grayed out. What you need to do, if you want to know, is if you wanted to do that, you have to go back to your equation, to insert, equation right here. This e to the x, these are choices. So what we want to do is we want to have one with C4. So we could put the C4 in here like this. Okay, and we could do the same thing for H3. So again, you just use those commands right there. It's kind of tedious to do, but it's worth it when you're writing up labs in chemistry. So I'm not going to do the rest, but you got the general idea, right? So the products over the reactants, this would be a negative right here, and that's positive. So I'll just do it right here. For this one, oxygen, again, what you do is you get to the equation editor. Let's not do that. Didn't like it. Oh, here it is. Okay, so I'm going to do that for this guy. So now that's what I'm going to choose. Just got to get rid of this other box. Ah, okay, I think you get the idea that we have to put plus. Since I told you this is kind of tricky, okay, and I wasted a little time on this computer, so we accelerate this. Okay, so H3O plus right there. Okay, so this is the equilibrium expression. Now, what is the equilibrium concentration of H3O plus given the pH? This is a hint right there. So all you have to do is 10 to the minus 2.34. Write this in a scientific notation. Okay, you have to write this in scientific notation, or else you won't be able to calculate Ka. So this has to be written in scientific notation. I believe this is 4.6 times, let's do it. Second function log negative 2.34. This will give you 4.57, but of course there's only 2 sig figs. Remember the 2 in the front does not count. It's 2 sig figs. This is 4.6 times 10 to the minus negative 3 molar. That's all you have to do. Now, the next one, this is exactly the same thing. So what we have in this equation, if we know the concentration of H3O plus at equilibrium, we know the concentration of the conjugate base, which is exactly the same thing. And this is what you're supposed to do. And if you went one step further and said the concentration of H3O plus is equal to the concentration of the conjugate base, which is this guy. Okay, so that's the conjugate base. They're equal at equilibrium. Oops, keep on doing that guy. Squiggly line. Okay, and this would be a added bonus mark. I add bonus marks everywhere if there is possible. And so now you fill out this table. Initially, remember, read the question again. We found the initial concentration of, excuse me, I found initial concentration. Water, we don't count it. This is a liquid, so it doesn't count in equilibrium. It's actually equal to 1. The initial concentration of these two products will be 0. The X is going to be a small amount of the acid dissociates. So that's why it's minus X. This will be plus at 2X. Equilibrium, the stoichiometric coefficient is 1. So that's why it's only plus X. And then you go and say minus 2.1 minus X. And these guys are X and X. That's how you get 3 marks. Now the rest, calculate Ka. All you have to do, take this formula, put it down here, fill in the numbers or fill in the values of this down here from what we found. We got 4.6 times 10 to the minus 3 for both of them. So we'll put that in. Okay, 4.6 times 10 to the minus 3. If you don't put in the m, that's no big deal. But that's the concentration. And that is the value of x. So you take 0.216, 0.216. You cannot say that you're assuming that this is going to be a very small number for x, not here. Can't say it here. So because when you subtract this, okay, 0.00046. Okay, what is that going to give you? 0.216 minus 0.0046 is equal to 2. This is going to give you a value of 0.2114. But we just need 211. We could put 2114 if you want, but it's basically 0.21. 3 sig figs right there, because that is the limiting number right here. This is a limiting digit, so it's 0.211. So now when we put in these values, 4.6 times 10 to the minus 3 squared divided by 2.211, this is 1.0 times 10 to the minus 4. Okay, so we'll do another review of the midterm of the final exam on Monday. Okay, good luck.